And if you also record. Great, so let's get started. So we have today Maissam Barkehsli from University of Maryland, and it's a great pleasure to have him here. And he'll tell us about defects and higher symmetries in 3+1 dimensions and topological phases of matter in that dimension. Okay, thanks. Please take it away. And the seminar, if you're new to this, actually, we have the policy. You can unmute yourself and ask questions whenever, or type it into the chat. I hope that's okay with you too.
Okay, yeah, great. So yeah, thank you for the invitation to speak here. Let's see. Okay, so I'm going to be talking about mostly this new paper that we posted a few months ago. And so this is a pretty large collaboration. This paper was with Ryohei Kobayashi, Yuan Shen, who are both JQI fellows at University of Maryland, and postdocs. And Shengji Huang was a JQI postdoctoral fellow, and now he's moved to Max Planck as of a month or two ago. There's Nathana Tantavasi-Dakarn, who was a PhD student at Harvard, and he just moved to Caltech. Guanyu Zhu, who's a researcher at IBM. And recently we started collaborating also with Po Shen, who's a postdoc at UCLA. He wasn't involved in this earlier project, but he's now working with us on some follow-ups to this as well. So one thing I find amazing about this field is that we're studying kind of very similar things, but from very different perspectives. So we're generally interested in this question of like, what are topological phases of matter? How do we understand them? And so this touches many completely kind of different subjects. Well, they're not actually completely different. One is condensed matter physics, which is where I come from, which is there we're trying to understand gapped quantum many-body phases of matter. And what we've discovered over the last few decades is that the universal properties of gapped many-body phases of matter are at least partially captured by topological quantum field theory and higher category theory. So I find it just incredibly amazing that these rich higher categorical structures are somehow emerging out of these complicated many-body quantum systems. And I think it's one of like the great interfaces between pure mathematics and physics. So in condensed matter physics, we're thinking of that we have many-body Hilbert space, and it decomposes as a tensor product of local Hilbert spaces. So often we're imagining these local Hilbert spaces might be sites on some regular lattice in d dimensions. And we're interested in local Hamiltonians, and we're interested in gapped Hamiltonians, meaning that you might have some ground state degeneracy, but then there's a finite energy gap in the limit that the system size goes to infinity between the ground states and the excited states. And often we're also interested in the situation where this, we can call this Hamiltonian the UV or microscopic Hamiltonian. We're interested in situations where this UV Hamiltonian has a symmetry, meaning that there's some symmetry, usual symmetry operators that commute with the Hamiltonian. Now there's a completely separate area where this stuff comes up, which is in the field of quantum error correction. There you want to encode logical qubits in some large collection of physical qubits. And there, the usual paradigm is that you have some collection of stabilizers, SI. These stabilizers all commute with each other. The logical code subspace is the subspace of the Hilbert space, where you just have +1 eigenvalue for all the stabilizers. And in the language of topological phases of matter, this code subspace is really the ground state subspace of a topological phase of matter. And then there's this important quantity, the code distance, which is the minimum support of operators that can take you from one logical state to another logical state. So you look at all the operators that can take you from one logical state to another, and you look at basically the smallest one. And the support of that smallest one is the code distance. Now, what people in this seminar might be more familiar with, I don't know, is that we also have the framework of topological quantum field theory, which is some functor from some Bordism category to category vector spaces. And then there's mathematicians approaching this subject, not only from TQFT, but from the language of what's called quantum algebra or higher algebra, where people are starting to study these fusion N categories. So let me just give you a few words about gapped phases of matter. So here, when we say the two Hamiltonians realize the same gapped phase of matter, if and only if there's a continuous path of Hamiltonians between them without closing the energy gap. And often we'll be talking about bosonic phases of matter versus fermionic phases of matter. So when I say a bosonic phase of matter, what I mean is that the total Hilbert space decomposes as a tensor product of local Hilbert spaces. And all the local operators on each of these local Hilbert spaces are bosonic, meaning if you look at operators from different sites, they necessarily commute with each other. However, even though we might often be talking about bosonic phases of matter in this sense, the emergent excitations can have all kinds of statistics. And in particular, you can have point-like excitations above the ground state, which are fermionic in nature. So then we have fermionic phases of matter. Here, these local Hilbert spaces are Z2 graded by fermion parity. So on each of these local Hilbert spaces, we also have some collection of local fermion operators. Like in this case, we could have some collection of Majorana fermions, which anti-commute with each other. And in this case, when we talk about symmetry, the whole notion of symmetry is a little more rich because there's actually there's two symmetry groups. There's a bosonic symmetry group, and then there's a fermionic symmetry group. The bosonic symmetry group is the group that acts non-trivially on bosonic operators, and the fermionic symmetry group is the group that acts non-trivially on the fermionic operators. And they're related to each other by modding out by this total fermion parity. So the fermionic symmetry group is really an extension of the bosonic symmetry group by fermion parity, which is just some Z2 group. And that extension is classified by this second cohomology class. In terms of quantum field theory, what we call a fermionic phase of matter, quantum field theorists would call a quantum field theory that depends on some background spin structure. Now, when we think about gapped phases of matter, there's several different distinctions that we make among gapped phases of matter. There's one class of gapped phases of matter which is going to play a particularly important role in my talk, which is invertible phases of matter. Invertible phases of matter are defined in the following way. A gapped Hamiltonian will realize an invertible phase of matter if its ground state has some kind of inverse state, which is labeled psi inverse, such that if you stack the two systems, so you consider this total Hamiltonian, then the ground state of this total Hamiltonian, which is going to be the tensor product of psi and its inverse, this is continuously connected to a trivial product state. So that's the notion of an invertible phase of matter or an invertible state of matter. And these invertible phases of matter they have some interesting structure. In particular, they form an abelian group under this operation of stacking. So if you imagine you just take two layers and you view it as one layer, then you get another invertible phase, and this forms an abelian group. There's a subclass of invertible phases of matter. So we call these symmetry protected topological states, or SPT states for short. So these are states where you have some G symmetry, but these states are actually completely trivial. They're continuously connected to a product state if you allow the G symmetry to be broken by your path of Hamiltonians. Whereas if you require that the path of Hamiltonians always preserve the symmetry, the state may become non-trivial. So this SPT states is just a subclass of invertible states, because you can see that for SPT states, you don't even need some inverse. It's already directly connected to a trivial product state if you forget about the symmetry. Right. So these SPT states, they can be characterized in the language of topological quantum field theory by an invertible TQFT. So this is a TQFT where you have some path integral, and it would depend on a background G gauge field because we have G symmetry, and there would be some spin structure dependence as well if you have a fermionic phase of matter. And invertible at the TQFT level would just mean that the magnitude of the path integral is 1. So the conjecture, I think it originated from Kapustin, and then many others have built on it and worked on it. The conjecture goes like this. It says that if you have, if you want to classify SPT phases in capital D space-time dimensions, the conjecture is that these are classified by Bordism theory. In particular, you take the Bordism group in D space-time dimensions, equipped with maps to a classifying space for the bosonic symmetry group. And then also your manifolds are all equipped with a spin structure. But if you have symmetries, it's actually not just an ordinary spin structure, it's kind of a twisted spin structure. So the twisted spin structure is defined by like this equation. You basically, the D of the spin structure is given by the second Stiefel-Whitney class plus the first Stiefel-Whitney class squared, plus the pullback of this omega-2 that defines the fermionic symmetry group, pulled back by just the background GB gauge field. So there's a conjecture that, then we look at this Bordism group, and then we take the torsion part of it. The conjecture is that SPT phases are classified by this Bordism theory. And then the conjecture continues, invertible phases would then be classified by the Bordism group in D space-time dimensions, the torsion part of that, but then you take the free part in one higher dimension. Okay, so this conjecture at least seems to be, we think it's correct in at least 1, 2, and 3 space dimensions. Although I think there's also people who still doubt that. But it seems to agree with a lot of checks in multiple different ways. And in particular, the lower the dimension you go, the more we have confidence in it. In particular, in 1+1 space-time dimensions, there's arguments and proofs from very different angles that essentially establish this fact. So in 1+1D, we know that all gapped phases of matter are invertible. So there's no non-invertible phases of matter, non-invertible gapped phases of matter. But there's this little subtlety here, which is that I'm assuming that if our Hamiltonian has some G symmetry, that G symmetry is preserved in the ground state. So I'm ignoring any kind of spontaneous symmetry breaking. If you include spontaneous symmetry breaking, then the description is a little bit more complicated, but the formal description, but the physics is kind of, we already understood. You just focus on the part of the symmetry that's preserved. So we know that all gapped phases of matter modulo. Yes.
Hi, Mason. If this statement, isn't it equivalent to a somewhat stronger statement that I'm asking whether it's equivalent, that there is no local operator acting in the space of ground states? That's a stronger statement than what you said.
Yeah, I think that's a stronger statement. Yeah. So I agree with you. Yes. Without question.
You agree that it's equivalent, or you agree that it's not? What you said is a subset of what I said.
It seems to be stronger. So you're saying there's no local operator that acts non-trivially in the
stronger than yours. So stronger, which means that I exclude more cases. It doesn't have to be associated with the symmetry.
I mean, I guess in print, if I didn't know anything, I would have thought that I could still have non-invertible gapped ground states, but local operators.
What you want is the system to be robust under small deformations of the microscopic Hamiltonian.
That's right, but non-invertible phases in principle could satisfy that, like in higher dimensions as well. But then if you go down, is your question specific to 1+1 dimension or?
No, it's in any number of dimensions. This is a difference between mathematicians and physicists. Mathematicians do consider TQFTs in 1+1 dimensions.
Yes.
And the reason is that they do not impose this extra requirement. So then there's a question about how to formulate the extra requirement.
Okay, well, on that topic, what I would say is that TQFTs don't really describe gapped phases of matter directly. You have to look at deformation classes of TQFTs. And if you allow yourself to continuously tune like some parameters in your TQFT, then you can get to an invertible TQFT even in 1+1 dimensions.
Okay. So that's okay. Thank you.
Yeah. But I think just the statement that there's no local operators which act non-trivially in the ground state subspace, that's stronger. And in particular, it doesn't distinguish invertible from non-invertible phases. Like in 2+1D, we can have non-invertible phases, but still there are no local operators that take one.
No, my comment was in the opposite direction. That if
whether
the local operator, if there is a local operator.
Oh, I see.
If there is a local operator acting in the space of ground state, then your comment about the deformation class enters in.
Right. Yeah. So if there are local operators and the state is not an invertible gapped ground state, I'd say. But then there's this then there's this issue of spontaneous symmetry breaking. So we have to do modulo the spontaneous symmetry breaking.
No, but then it's included because the order parameter for the symmetry breaking would be that local operator.
Yes, you're right. Thank you.
Sorry for you.
No, that was great. No, I encourage everyone to interrupt as much as possible. It's more fun to have a discussion and everyone will be on the same page. Thank you. So, okay, so where was I? So for bosonic systems, it's now established that SPT phases are the same as invertible phases in 1+1 dimensions. And these are classified by this second cohomology class or second cohomology group with U1 coefficients. And physically what this mu2 means, this second cohomology class, is that it basically captures the projective representation formed by zero energy edge states of the system on one spatial dimension. And the TQFT path integral, well, you have to maybe normalize it appropriately, but it can be described, it's a path integral which depends on the background gauge field. It can just be described by pulling back the cohomology class onto the manifold using your gauge field. Now, there's a subtlety here. Often when you hear mathematicians or sometimes field theorists talking about this, they're implicitly assuming G is finite, but we don't need G to be finite. We can allow G to be continuous as well. And in this case, the belief is that we should be, what we mean by group cohomology in this case is called Borel group cohomology, where the cochains are assumed to be measurable. So we think this is the same as just requiring the cochains to be piecewise continuous, but there's like a piece of kind of classical mathematics that I think I've never heard anyone talk about, which is whether to what extent measurable cochains and piecewise continuous cochains are the same. And I think this is actually a relevant issue for if we want to better understand kind of how we apply these things in physics. Now, for fermionic systems, it's actually much more complicated. They're still all gap phases are invertible, but here we understand the classification in terms of a set of data. Of course, before we had the Bordism classification, but that's very abstract, and it's hard to actually do anything with that Bordism calculation. It doesn't really give any insight into what the physical properties are of these systems, and it's actually hard to even compute the classifications. So what we've done is we've converted those Bordism calculations in many situations into concrete set of data and consistency conditions where we can physically interpret what it all means. And I think it gives kind of an alternative, almost derivation of that Bordism classification, if you will, because you can often derive this data and consistency conditions in completely different ways. So here the data is there's N0, which is some Z2 element. There's an N1, which is a 1 cochain on the group Z2 valued. And then there's a mu2, which is a 2 cochain on the group, which is U1 valued. And the consistency conditions, there's some consistency conditions that you can derive. They look like this. There are some equivalence relations involving these consistency conditions as well. And then you can also derive how the stacking law works. So you can derive the full abelian group structure. And that was done in this paper. And physically, if we just look at some examples here, the 1, 0, 0 element here is what's called the Kitaev chain. That's a chain where sort of you have Majorana zero modes on the edges of your system. And that's an invertible phase, but it's not an SPT. And then if the first 2 entries are 0 and you have this mu2, then that's just, we're back to basically having a bosonic SPT. So you're forgetting about the fermions entirely. And that just goes back to the group cohomology classification. And if you have this N1 in the middle, 0, N1, U2, then that forms an interesting fermionic SPT. So it's an SPT is a subset of invertible, and that this is kind of the lingo here is this is what we now call group super cohomology. And sort of this kind of was introduced by Zhengcheng Gu and Xiaogang Wen in 2014. Now, if you go up.
Can I ask a quick question? Sorry, it'll be a quick question, very quick. It's about your classification of these invertible phases of matter. You suggested it's sort of related to a Bordism group, and I'm a little confused because I seem to remember that invertible TQFTs are classified by a different kind of Bordism group, sort of a dual of a sphere. So
Right.
is there something here that is there a discrepancy? Does it have to do with fully extended TQFTs or something of that sort?
So there's two subtleties here. The one subtlety is whether you're talking about SPT phases or invertible phases. So if you remember here, there's SPT phases are classified by the torsion part of the Bordism group. The invertible phases are the torsion plus the free part. So sometimes people call this like okay, really what you want for the TQFT is a map from this into U1. So people say that's the Anderson dual of
That's
the
exactly right.
Bordism
Okay.
spectrum.
Got it.
Yeah, so that's for invertible phases. And then, but if you specify if you restrict to SPT phases, then you just can forget about that free part.
Okay, I think what you've really written there is a different way of presenting the same information.
Yeah. So this is the one I'm kind of comfortable with because I'm not really a high-level mathematician, but I think the more sophisticated way of saying it is, yeah, it's some Anderson dual of the Bordism spectrum.
Got it. Thank you.
Okay, so then 2 plus 1D invertible phases. These are, we believe these are classified by an element of the third cohomology class. But this is the SPT part of it. So that was a torsion part of the Bordism group. And then there's this extra Z, which comes from the free part. And this is interesting. It's generated by what's called the E8 phase, or if you're familiar, like E8 level 1 Chern-Simons theory. But the interesting thing about this is I think this, this seems to just beyond TQFT entirely. I mean, not entirely, but part of this Z is beyond TQFT. So I think this is the first example of properties of phases of matter that are beyond TQFT is some parts of the Z. In particular, I think if you have 3 copies of this E8 phase, my understanding is that TQFT cannot detect it. So it's interesting point. And then the path integral for these things is given over here. So 2 plus 1D fermionic invertible phases, we also kind of recently understood the full set of data and consistency equations and equivalence relations. So here, remember that we had a fermionic group. So that was classified by this second cohomology class. And then there's also this S1, which is basically tells us which group elements are unitary or anti-unitary. And so it's like a Z2 grading on the group elements. So here the data consists of 4 quantities. There's the chiral central charge, which has to be multiple of a half, integer multiple of a half. Then there's this N1, N2, and U3, which is given here. And there's more complicated consistency conditions that you can derive now. And in particular, like there's this O4 obstruction, which we know the general formula for this O4 obstruction, but in some special cases, it looks like this. And then there's some complicated equivalence relations. And I'm not even going to try to show you the stacking law because it's even more complicated. So here, the chiral central charge being 0 implies that this system is actually just a SPT. Whereas if the central charge is non-zero, it forms this non-trivial invertible phase of matter. Okay, so there's one thing that I'm going to be using quite a bit, which is dimensional reduction. If you take a 1 plus 1D G symmetric invertible phase and you put on a circle, and then you put you put a G holonomy around the circle. So you imagine there's kind of some G flux in the center of the circle. So when you go around, you get acted on by G. Then if you just view this as a 0 plus 1D system, you do dimensional reduction, then what you get is you get just a 1D representation of the centralizer of G. So mathematically, there's this slant product which can take us from the second cohomology class into the first cohomology class of the centralizer of G. In general, slant product does more. It just gives us an H1 of G U1. But here I'm only going to use the map to this smaller group, the centralizer of G. And specifically, that map looks like it's just the ratio of these 2 cocycles. And physically, what this is saying is that if I have a G flux through the circle, essentially I'm getting a 1D representation. So I'm getting a abelian charge that's bound to this G flux. And maybe a little more formally, you can think about the path integral on the 2 torus, the space-time path integral on 2 torus, with G and H holonomies along 2 cycles. You take G and H to commute with each other. Then you get you can view this as just the path integral of a 0 plus 1D space-time dimensional system labeled by G. And so, yeah, on just a circle. And then there's this point that the actually the charge that you get really doesn't depend on G itself. It only depends on the conjugacy class of G. So you can show that. So really what we're saying is that you get some abelian charge for some conjugacy class of G that's threading the circle. Now, if you instead compactify like not just a bosonic SPT, but a fermionic phase. So suppose you compactify this 1 plus 1D Kitaev chain. Then you can compactify it with even or odd fermion parity flux threading the ring. And if you do, depending on whether you put even or odd fermion parity flux to the ring, the ground state of the effective 0 plus 1D system will have even or odd fermion parity. So this is a fact that I'll use also. So now let's go up a dimension. Let's go to 2 plus 1D non-invertible bosonic topological phases. We did invertible. So these are classified by, we think that they're characterized by two quantities, a modular tensor category and the chiral central charge. And the modular tensor category determines part of the chiral central charge. Depending on your definitions, it would determine it modulo 8. So here, the isomorphism classes of simple objects in this modular tensor category are what we call particles or anyons or point defects. And they have these familiar data that I think by now almost everyone knows, the fusion rules, F symbols, R symbols, topological twists, and modular S matrix. So there's a recent paper that I like a lot from a couple of years ago by Kyle Kawago and Michael Levin, where they kind of start to develop some ideas of how we can actually extract this modular tensor category data from a quantum many-body system. Like exactly what do you have to do to extract this data? And this is a very non-trivial question, which I think more attention should be given to. Now, here in condensed matter, we often talk about these non-invertible bosonic topological phases where there's no symmetry. But when we say no symmetry, what we mean is that the UV Hamiltonian that we're thinking of, or meaning the Hamiltonian of that microscopic system, does not have any symmetry. But the ground state subspace itself does have a kind of symmetry. In particular, there are operators that you can act on the ground state, which give you the ground state back. And you know, there's a nice paper by Hastings and Wen where they kind of describe this by quasi-adiabatically continuing from some exactly solvable models. So in particular, there are loop operators, WA of gamma, and if you take gamma to just be a contractible loop in space, then it preserves the ground state up to maybe an overall factor, which we'll call the quantum dimension. And then these operators form interesting algebras. They form some fusion algebra. You can take interesting products, like there's this twist product that you can define, where you essentially interchange the order of the operators where they overlap on one of the overlaps in one direction and then in another direction on the other overlap. And this should be proportional to the S matrix. So what I like, you know, the kind of modern way that I like to think about this is that what we really have is that a topological phase here has kind of an infrared modular tensor category symmetry. So this is kind of emergent symmetry because the microscopic Hamiltonian did not need to have this symmetry. So you can call it IR symmetry, you could call it emergent symmetry. It's just the property of like the ground states and the ground state subspace. Of course, there's a refinement on this, which is actually it's a spontaneously broken infrared symmetry, because if you can also take the loops to be non-contractible and then they act non-trivially in the ground state subspace. So recently, we did some work where we showed, where we started to develop this program of maybe we can search for these symmetries in quantum many-body ground states, like set up some ansatz for operators and just directly do some numerical optimization and search for these kinds of symmetries. And I think that's a very fruitful direction in discovering emergent symmetries, these emergent categorical symmetries in quantum many-body systems. Okay, so the invertible objects, meaning the abelian anyons, they are associated with unitary or invertible loop operators. So, you know, they keep the ground state invariant and they're unitary in the ground state subspace. So they form an abelian group under fusion. And the modern way of thinking about this is that it's really a one-form symmetry of your topological field theory. And then the braiding of the anyons you can think of as a 't Hooft anomaly for this one-form symmetry. But this modular tensor category, what we've realized over the years is that it only captures part of the information of this topological phase of matter. It captures only the braiding and fusion of the point defects, which in 2 plus 1 dimensions are codimension 2 objects. But there's also line defects, and there's gapped line defects, and they have a lot of interesting properties. And we sort of came at this from condensed matter physics, and we found many interesting examples in the context of fractional quantum Hall states and quantum spin liquids and things like that. And we realized that there's like a lot more to the story when it comes to universal properties of these topological phases. So what we now know is that these gapped line defects in 2+1D, they form part of a more complicated algebraic structure, which you could call a fusion 2 category, or sometimes you call a monoidal 2 category. And the first place I heard about line defects forming monoidal n categories was in sort of a talk that was written up by Kapustin in 2010. I'm not entirely sure what the history is. Mathematicians use the word fusion in a very specific way. So you could say monoidal 2 category, but fusion has some extra properties like finiteness and semi-simplicity and so on. And it's very, very difficult to properly work out what these notions of semi-simplicity and so on are. So that was what was done in this paper by Douglas and Reuter. And so this fusion 2 category is sometimes called mod C. So mod C, as a 2 category, what is its properties? Well, there are zero-morphisms. It's a 2 category, so we have 0, 1, 2 morphisms. The zero-morphisms are codimension 1 defects. So these are, you can think of them as gap domain walls in your system. These would be module categories. So an object of the 2 category mod C is a module category. And the fact that it's a monoidal 2 category, fusion 2 category, means you can fuse these defects together. And there's some interesting fusion rules for these domain walls, which no one ever...
Just make sure that we're on the same page. When you say line defects, this is codimension 1 in space or codimension 1 in space-time?
Thank you. This is codimension 1 in space. And it's codimension 1 in both space and space-time, but it's a line because when I say line, I mean in space.
Okay, so just to make sure, when some people say line defect, when it's, in this case, it's codimension 2 in space-time, either along space or time.
Yeah, so
the lines of the Wilson lines of the Chern-Simons theory are also being referred to as line defects.
Yeah, so we probably would call them surfaces.
Yeah.
I just want to know which one you use. So these are really surfaces.
Yes.
These are really surfaces in space-time.
These are surfaces in space-time. And I'm going to try to be careful and just use codimension 1 to not have the ambiguity. So I guess when I say line defect, I'm really thinking just as a condensed matter physicist, something in space.
Okay.
So then we have 1 morphisms. So these are codimension 2 defects. So you can have one domain wall, and then you can have a boundary with another domain wall, and that itself has an interesting label. So that's the 1 morphism. And mathematically, these are functors between the module categories. But because it's a fusion 2 category, then you can have interesting junctions as well, because you can fuse A and B. There's some 1 morphism that takes it to C, and so on, things like that. Then you have 2 morphisms, which are the maps between codimension 2 defects, and then you start to get more interesting structure. You can have these domain walls, and then there's a map from this sort of network to this kind of network, things like that. So this is a very rich, interesting structure. And I would say, mathematicians kind of defined this fusion 2 category and said that mod C is an example in kind of abstract sense. I don't feel like this is really understood at the level where you could really write down all the data, put it into a computer, and calculate really a lot of concrete things with it. Okay, so now these domain walls, some of these domain walls can be invertible and some of them can be non-invertible. So the invertible domain walls, they form a group. That group is called AUT-C. It's the group of braided autoequivalences of the modular tensor category. So here, an element of AUT-C has a property that when it acts on an anion, it can permute the anion when the anion passes through the sheet in space-time. And it has the property that it preserves the modular S matrix and the topological twists, and it preserves the F and R symbols up to a gauge transformation. But that's not all. There's more information as well. There's an action on these fusion and splitting spaces of the modular tensor category. So you have these spaces like V, A, B, C, and of course, when the map acts on it, it permutes the labels. But also, this is just a non-trivial map in general. So if you pick some basis on either side, you have a set of symbols, which we call U symbols, which effectively act on this vertex as you pass the sheet through the vertex.
Sorry, can I just clarify what the VABC is? A, B, and C are now surface defects, and there's a junction, and that's that.
ABC here, ABC are like these are codimension 2 defects.
Okay, so these are actual line defects first.
Right, these are lines in space-time.
Okay.
And then when one line C splits into two lines A and B, there's a vector space here.
Sure. And that's this vector space V, and then rho acts on these junctions. That's what you're saying.
Yes, exactly. Yeah. So this is not an important non-trivial data part of this rho. So what we have is that the invertible anions, they define some like IR one-form symmetry group A. The invertible domain walls, or the invertible codimension 1 objects, they define an infrared zero-form symmetry group, which you could say is this Brady autoequivalences. There's also a third cohomology class that enters the discussion. And once you know all of these U's, we have explicit formulas for how you can calculate this O3 cohomology class. So that was described in our paper in 2014. And after that, we found many other interesting examples where you have non-trivial third cohomology classes appearing here. Now, altogether, this defines.
Sorry for being such an asshole, but I understand what you said about the automorphism. What I don't see is how it is connected to other zero-form symmetries that can act. So, for example, in the fractional Hall effect, where there's U1 level 3, we can couple it to a group, which would be U1, and the anions have charge a third. Does this fall into?
I'll mention that in a minute. I won't really get into that, but I'll address your question in like 30 seconds. Right, so altogether, this defines what's called a 2 group. So we have this OT A, we have this third cohomology class. We also have an action of OT on A, which I didn't write explicitly here, but that's part of the information of the 2 group. So you could say that this kind of a TQFT and 2 plus 1D in general would have an emergent 2 group symmetry or an infrared 2 group symmetry. Now we can always promote any regular old group into a 2 group by just kind of making these extra pieces trivial. And if we have an underlying microscopic Hamiltonian and it has a G symmetry, then we need to define, and so that's like a UV symmetry of the system, this G. Well, what we do is we just promote this G to a 2 group, and this 2 group in this following way, and then we need to define a map from kind of the UV 2 group symmetry to the IR 2 group symmetry. And this map is, a very non-trivial thing, and it's hard. You have to do a lot of work to really understand the details of this map, and that's part of what's done in this paper. But at a high level, this is how you can describe it. So Nadia, I think this is supposed to answer your question, because in the fractional quantum Hall effect case, you can just take your G to be U1, and then you can think about abstractly as the way that U1 acts in the TQFT is by some map from U1 thought of as a 2 group in kind of a trivial way, and you map it into this IR 2 group symmetry. And all the devil is in the details of what it means to have this map.
But this is, if I go back to your few lines up, where you define the automorphism with an underscore.
Yes.
If I didn't know it came from a microscopic theory, how would I describe it? The U1 is not an automorphism of U1 level 3.
Well, there the U1 maps trivially into OT, and so then when you want to define this map, there's a bunch of data that you need to specify. In particular, you need to specify if I have a junction of a G sheet and an H sheet and a GH sheet, what happens when I pull the anion line through that junction?
No,
that
I'm
information.
Interested in the UV. I'm a low energy person, not interested in the UV. And I would have guessed that in the line that starts with altogether this defines, you should be able to accommodate that U1 in some form, because I can couple the TQFT to a U1 background gauge field.
But I think that's just like, this is just saying that your field theory has this is the IR symmetry of your field theory. You can always couple a field theory to a bigger symmetry group, but to do it, you have to specify a map from that bigger symmetry group into the IR symmetry of your field theory.
Yeah, but there's a non-trivial fractionalization class for the anyons. It's
right.
a third, not a fifth.
That's encoded in this map.
Mhm.
So that's
Okay,
why I said
thank
that
you.
wasn't details. That's all encoded here. Right, and this map, you can only do this, obviously, if you want to match these up, you need the cohomology class. If this is just a regular group that you promoted to a two group in this trivial way, you need this O3 to vanish. So in this sense, an O3 is actually an obstruction to having your symmetry, kind of just be an ordinary UV global symmetry group. Okay, so we found that we have this IR two group symmetry, but there's actually a lot more structure here. It's not just the two group, there's more structure. Because remember, when I drew these diagrams earlier, I had a fusion two category of defects, and they had zero morphisms, one morphism, two morphisms. So mathematicians define what's called a categorical two group, and that's just all the invertible piece of this mod C. So that is sometimes denoted as this OT with two underlines. This is a more complicated structure, and it has all this extra data, which if you just know about A, OT C, and this third cohomology class, you won't know that there's all this extra structure. So two group is not, the full IR symmetry is not even just the two group. It's kind of this more complicated structure, which is this categorical two group. Yeah. So that's just the comment here. Okay, so let me give you a quick example. You take Z2 gauge theory in quantum information literature, sometimes called Z2 toric code. So here we have four types of particles. There's the trivial particle, the Z2 charge, the Z2 flux, and then the composite of the two, which is a fermion. Here we have 6 types of codimension 1 defects. There's the trivial one, which I didn't draw. And there's the interesting invertible one, which is the focus of my talk, which is that when an E particle goes through this domain wall, it becomes an M particle. Or another way of saying it is that when an M particle goes, well, how do I say it? Oh, when an E particle goes through, it becomes an E particle. Actually, I should have done it the other way. When an M particle goes through, it becomes an M particle times a fermion. That's a way of understanding this twist string, or this defect. And I'm going to call this kind of defect a twist string because it kind of twists one particle into another. This is an example of an invertible domain wall. All of these other domain walls that exist are non-invertible domain walls. So you can have the E charge, the Z2 charge condensing from both sides, Z2 charge condensing from one side, magnetic flux condensing from the other side, and all the combinations. These are all non-invertible domain walls. So this EM twist string we can understand from what's called gauging. So we can start with a trivial 2+1D fermionic phase, and we can gauge the Z2 fermion parity symmetry. And if we do that, we get just Z2 gauge theory. And in this Z2 gauge theory, we can interpret the M particle as the Z2 flux, and the fermion is what we would interpret as a Z2 charge. So the way that we can, in particular, get this EM twist string is we can start with a trivial fermionic phase, and then we can put a codimension 1 defect, and we decorate it with this Kitaev chain that I had mentioned earlier when I was describing 1+1D invertible fermionic phases. And now, overall, this is just some fermionic phase of matter, and I can gauge fermion parity now. I couple it to a background fermion parity gauge field, and I just make it dynamical. So in the field theory language, this would be like sum over all spin structures of the theory. And then we just get Z2 gauge theory, and now this string becomes this EM twist string. So let me explain what happens or why that's the case. Well, when I take this M particle, this flux, through this invertible domain wall, because the domain wall is invertible, I can just kind of like snap this up and cut it off. And then I get this picture. And now what is this picture? This is my 1+1D Kitaev chain, but compactified on a circle with a fermion parity flux through it, which means that it should have odd fermion number. And so that odd fermion number is why we have an extra fermion over here. So that's the mechanism by which M becomes M times psi, which becomes E. So let me give you another example. We can take Z2 cross Z2 gauge theory. This has an interesting automorphism where you preserve the charges, but you take the M1 flux to M1 times the E2 charge and vice versa. And you can understand this, a twist string that acts by this automorphism, by starting with just a trivial bosonic phase, decorating a 1D line, with a Z2 cross Z2 bosonic SPT. So Z2 cross Z2 1 plus 1D SPTs are classified by the second cohomology group, which takes values in Z2. So I'm just taking the non-trivial one and decorating it on this string. So this is sometimes called the cluster state, this particular SPT. So then we gauge. And that gives us this kind of automorphism group. And actually, you can show that in Z2 cross Z2 gauge theory, all of the invertible codimension 1 domain walls can come from these kinds of procedures, where you start with a trivial bosonic or fermionic phase, you decorate a domain wall with a bosonic or fermionic SPT or invertible phase, and then you gauge. And you can show that all of the invertible codimension 1 domain walls arise in this way, in Z2 cross Z2 gauge theory. But it's not true in general. It's not true in general that all kinds of invertible codimension 1 defects or twist strings come from gauging bosonic or fermionic phases decorated with 1 plus 1D invertible phases. Let me give you a counterexample. You can take Z3 gauge theory and consider electric magnetic duality in Z3 gauge theory. There, M would go to M times psi, which is now E particle. But psi is not a fermion. It's some anion, it has fractional statistics, and it has order 3. And this is not something that you can get by decorating with 1 plus 1D invertible phase.
Is there a way to construct the EM domain wall in toric code without introducing fermions, just purely in a bosonic system, by some kind of condensation, or is it?
I mean, there are other ways of thinking about how you get this EM domain wall. Like another way of thinking about it is that you've really condensed an E charge from the left, and then you've condensed the bound state of an E charge from the left and the M charge from the right. So when E goes to the domain wall, it can kind of couple with an object from that condensate, and then so the E part can disappear, and then M part can continue across. That's another way of thinking about this. But if your goal is to start with a trivial phase and gauge something, gauge a overall zero form symmetry, and then get this EM twist, you need to do it by this fermion domain wall decoration.
I see. There's no local modification plus gauging that will give this EM domain wall. You have to. Not
if you're talking about zero form gauging, like globally everywhere. I mean, you can think about this as maybe like higher gauging, which is more like condensation of this E left, M right on the domain wall. Okay, so now let's go to 3 plus 1D. Oops, I don't have that much time. So in 3 plus 1D topological phases, the particle and string excitations, the algebraic structure there should be a unitary braided fusion 2 category, is our understanding. But the topological defects, if we just extrapolate from 2 plus 1 dimensions, they should all combine to form a unitary fusion 3 category. Mathematicians haven't defined the notion of fusion 3 category, but there should be some notion, and maybe for now we can think about it as a monoidal 3 category. So here the codimension 1 defects are zeromorphisms, codimension 2 defects are string excitations or surface operators, surfaces in space-time. These are 1 morphisms. And then we have the codimension 3 defects, which would be 2 morphisms. And so our goal is ultimately, it'd be nice to understand this unitary fusion 3 category. And for now, but our goal is maybe we can just focus on the invertible parts, and we could fully understand the 3-group symmetry, which is formed by the invertible defects. Now, so let's go ahead and do this. So there's an argument by Tian Lan and Xiaoyang Wen that all 3 plus 1D topological phases of matter can be described by finite G gauge theory, coupled to either bosonic or fermionic charges. And so you just need to specify G, and you need to specify a 4 cocycle. So I'm going to, in this talk, just focus on, for the rest of the talk, just finite G gauge theory in 3 plus 1 dimensions with either bosonic or fermionic charges, and I'm going to take this 4 cocycle to just be trivial. So it's already well known that we have point charges, which are described by ereps of G. We have flux loops, which are labeled by conjugacy classes. We can allow the flux loops to carry charge. That's labeled by G, and then the erep of the centralizer of G. And so the abelian point charges, they can form a 2-form symmetry group. And so mathematically, we can just write the abelian charges are just homomorphisms from G into U1. And then the abelian flux strings are described by the center of the group. So you can ask, what else is there? And it turns out there's a lot else. There's a lot more. So in particular, there's new kinds of codimension 2 defects, which haven't really been studied that much before. They've been studied a little bit in some various contexts, which we can call them twist strings as well. There's multiple constructions for these twist strings. So I want to give you 2 constructions, the first 2 over here. And there's a much more powerful and general construction, which I won't describe. But I'm going to describe these first 2 constructions. So first is layer construction. So layer construction of 3 plus 1D gauge theory means you just take a 2 plus 1D gauge theory and you layer it, and then you condense charges from neighboring bound states of charges from neighboring layers. And what that does is that allows the charges to become fully mobile in in the third direction. And then what it also does is that it confines the fluxes in a given layer, so that that's not allowed excitation anymore, but it confines them all into a string. So these do commute with the condensate, the string excitations. So that's a way of constructing 3 plus 1D gauge theory. And you can do it for either bosonic charges or fermionic charges. Because for fermionic charges, you can just take bound states of the fermions in adjacent layers. And so if we draw this kind of twist string in one of the layers, then that becomes a twist string in the 3 plus 1D system. But there's an important compatibility condition that you need, which is you need the automorphism that's induced by this twist string to be compatible with that condensation that's giving rise to the 3 plus 1D G gauge theory. So let me describe a little bit more detail the case of abelian G. So here we pick some subset of the particles in the abelian G 2 plus 1D G gauge theory, which I'm going to call M. So M contains only bosons or fermions which mutually braid trivially with each other. And then for any anion that's not in M, there exists some anion B which is in M, such that A and B have non-trivial mutual braiding. And MAB is the mutual braiding phase between A and B. And then once you have these 2 conditions, you can show that M forms a group under fusion. And then you can go ahead and condense pairs. This is a layer index, so you can condense the bound state of A and A bar from neighboring layers. And what this does is that particles in A become fully mobile. These become your electric charges. And then the particles that are not in M, because they braid non-trivially with A, become confined, but all the B's can bind together to form strings, and these strings do commute with the condensate. So those are what we call the flux strings. So a flux preserving automorphism is going to be something that has the following property, which is that if any anion B goes through the twist string, at most it gets bound by some charge, basically, some element of M. So this is called flux preserving because after you condense these M's from neighboring layers, the fluxes are labeled by A modulo M. So this is essentially preserving the flux label, and just maybe at most it just attaches some charge as your flux crosses the twist string. And you can show that this flux preserving condition is equivalent to the condition that every A is completely preserved by the automorphism. This is a statement that the automorphism from this twist string commutes with the condensate. It just preserves all the things that are being condensed. Right, so and if we start with an invertible codimension 1 defect in 2 plus 1D, which implements this flux preserving automorphism, that gives us an invertible codimension 2 defect in 3 plus 1D. So now there's an interesting physical phenomenon that's happening. If a flux string crosses this twist string, then at the intersection, there's a point charge that appears at the intersection. Because if you think about this flux string, microscopically in the layer construction, it's just a bunch of these B particles, these anions, which are all bound together to form a string. And so as that string crosses this twist string, in the layer that you have a crossing, the B gets attached by an A, which was a charge. So at the crossing point, a charge gets nucleated and you get this point charge. The simplest example of this is actually if you just take regular Z2 gauge theory with fermionic charge in 3 plus 1D, then that EM twist string that we had in 2 plus 1D becomes a twist string in 3 plus 1D. And as the flux loop crosses that twist string, a fermion is nucleated there. So a way of drawing that is you take the surface operator that creates an M loop on its boundary. And if that crosses the twist string, then a fermion line can end on on that junction, that crossing point. And you can see this very clearly with exactly solvable models and just show everything about it. Okay, so now we can also generalize this now. This picture is nice because we can generalize to non-abelian gauge theory. And so again, we can have some flux preserving automorphism. So first of all, I should say, if you want to condense these charge anti-charges from neighboring layers in non-abelian gauge theory, it's a much more complicated thing. You need to pick some Lagrangian algebra and some appropriate modular tensor category. It's complicated, and we have a proposal for how to do this in our paper. But anyway, to get this twist string, now we want some flux preserving automorphism. So we want the automorphism to preserve the flux label, but just possibly permute the charge label. But it turns out this is not actually enough to guarantee that we get a topological defect. We also need another condition. Sorry, we need a stronger condition. I don't know, we just need a stronger, because this condition is strictly stronger than the first condition. And this condition is that instead of we just get some arbitrary permutation, the permutation that we get is by binding with some 1D representation of the centralizer. And right, so this is what we need. And the reason that we need this, we need to permute the charge by something that actually doesn't depend on what charge we started with. And the reason is because if we just had condition 1, you can imagine a situation where you have some irrep already on the string, some charge already on your flux string. And as it crosses the defect, it goes to another irrep. But if the permutation depended on exactly what pi g was, then you can imagine you kind of deform the loop a little bit. And now this particular point doesn't cross the string. And then you would get, and then you would not potentially get, or you get a different permutation. In this example, no permutation would happen. There's a concrete example here that comes from A6 gauge theory that's being drawn here. So if you just had the first condition, you could potentially have these defects that are still gapped invertible codimension 2 defects, but they're not fully topological because some properties of the physics would depend on exactly what was going on in the geometry. I think this is a really interesting situation because this is an example of a gapped invertible defect if you have 1 but not 2, where there's some underlying dependence on geometry. It's not fully topological. This is kind of reminiscent of fractons, for those of you who know what fractons are, because not everything is fully topological here. And so there's an example of this in A6 gauge theory that we found, where you can satisfy 1 but not 2. But anyway, we found some other examples where you do satisfy 2, and so this gives interesting twist strings in non-abelian gauge theory.
Before you go on, I still have a question about these layer construction. So you started with all these layers, and you did the whole thing. In the end of the day, do you still have the layers, or does the whole structure appear in a smooth space-time?
Well, so microscopically, you obviously would have the layers, but you would wind up with a phase of matter that can be fully described by a continuum TQFT.
So you end up with something where the layers are gone.
Yeah, so you can just think of this kind of layer construction can motivate exactly solvable lattice model. And so then you have the usual situation where you have a lattice model. That lattice model can realize some discrete G gauge theory, and then at low energies, you can forget about the lattice and it's described by a TQFT.
Right. And is it clear that no information about the underlying layers survives? For example, the foliation of the manifold that you have. So
well, we can. So this is not even a question specifically about layer construction, because we can use the layer construction to actually. We can derive the usual 3+1D lattice G gauge theory from a layer construction perspective. And so this is really just a question about to what extent is it clear that your lattice model for discrete G gauge theory
right, but
really
my question is really to show that, but to what extent are we sure that all the microscopic information is indeed irrelevant at long distances, and we have a continuum description with no more labels that are associated with that, with say the choice of foliation or something. It's something to be
Well,
shown.
in these, well, yes, that's right. But in these examples, we're pretty confident because we know the ground state subspace is finite. We know it exactly. We know the operators that take us from one ground state subspace
That's
to another.
not
So
really
there's
the case of the fractals that you mentioned.
right. That's not the case for fractons. But by the way, I mean, I should mention that the whole point of what I was just saying is that you can, even in these G gauge theories, you can write down codimension 1 defects that are not fully topological. No, sorry, codimension 2 defects, these string defects, which are not fully topological. They're still geometric. So you can, even in these theories, you can introduce defects that cannot be fully described by topological quantum field theory.
Great, thank you.
So, okay, so the second construction that I want to mention is this decoration by invertible phases. Okay, so I'm actually out of time, but do you mind if I go a few minutes over?
We don't really have that strong cutoff, so please, there are lots of questions, so I think we can continue for a couple of minutes, yeah. How many slides do you still have?
Well, I have like 20 slides, but I don't have to get through all of them. They were just in case. So the second construction is we take our 3+1D G-symmetric bosonic phase, we start there, and we take our 1+1D defect, and we decorate it with a bosonic SPT, and now we gauge G. So now we get some interesting invertible codimension 1 defects. And now we can understand what happens. We take a flux loop and we pass it through this twist string. Then again, it's kind of a picture that I drew before, but now 1 dimension higher, where you kind of wind up with a situation where you have your flux loop. Sorry, yeah, you have your flux loop, which is piercing kind of this circle of this 1+1D SPT. So by the dimensional reduction argument, this gives us an abelian charge located on the located over here, which you can derive from the slant product. And if it so happens that this flux loop is abelian, meaning it's the flux is in the G is in the center of capital G, then the centralizer is a full group. So we really get we get a 1D erep of the full group, not just of the centralizer of G. So then you can also decorate with fermionic invertible phases. So now you can ask, I gave you these two constructions. Are they equivalent? Can you get the same construction, the same things in both cases always? So we can partially prove this. We can show that the second construction implies the first construction. And because I'm running out of time, I'll just skip over it. And we can partially show that the first construction implies the second construction. And again, I'm going to skip over that. But if you're curious, I can tell you what we can show and what's missing. So we almost have an equivalence between the two, but we can't fully prove it. Now, okay, so there's an interesting question of what's the difference between these flux loops and the twist strings, because now you can view them both as, oh, they're just codimension 2 defects. What's special about flux loops as opposed to these twist strings? And ultimately, and in a real physical system, they're both similar in the sense that both of them would cost some energy that grows with the perimeter of the loop. But the main reason they're different is because flux lines have flux through them and you have flux conservation. So flux lines cannot end on the vacuum. Mathematically, you could say there's no two-morphism between the flux line and the trivial line. However, the twist strings can end on the vacuum. And if you allow them to end, then you get interesting non-invertible codimension 3 defects. So here you allow this 1+1D defect to end, then you get these interesting edge zero modes. You can get Majorana zero modes. You can get some projective representation of your group, because at the end of the day, this is the boundary of the 1+1D invertible phase. So this gives some interesting examples of non-abelian statistics in 3 dimensions. It doesn't violate old no-go theorems that people had, because these are happening. These are not deconfined objects. They are existing only at the endpoint of some codimension 2 defect. So there's an interesting example. This can give rise to like logical qubits. So this is useful in quantum error correction. I'll skip over that. So now what I want to tell you more about is, well, okay, so we have this twist string, we have the flux strings. So just on general grounds, from what we learned in 2+1D, there should be some kind of underlying categorical 3-group symmetry, which would be some invertible part of a fusion 3 category of defects. And for now, our goal will be, well, let's just try to write down what are the background field equations for this three-group symmetry. What is its 't Hooft anomaly? Maybe we can just fully solve this problem in this class of models. So we would have some zero-form symmetry, one-form symmetry, two-form symmetry. We could introduce background gauge fields for all of these guys. So let me give you a quick example. So we would go back to this G equals D2 cross D2 gauge theory with bosonic matter. Here we have a one-form symmetry, which would be the magnetic flux strings generated by the magnetic flux strings, and then these new twist strings. Then the full group here would be given here. And the two-form symmetry would just be generated by the abelian charges. So that's just D2 cross D2. So we can introduce background gauge fields. We can have a three-form background gauge field for the charges, which are E1 and E2. And that's a three cochain on the manifold valued in Z2. And then we can have a two-form gauge field for the magnetic flux loops, and then another two-form gauge field for the twist string. And basically, the point is that the fact that the crossing between the flux string and the twist string generated a charge, mathematically, you can describe in this way, which is that you look at the intersection between the sheet corresponding to the flux sheet in space-time and the twist string sheet in space-time. And there's a crossing point there. And that intersection has to be the source of electric charge. And so that's all put together in these equations. So you can kind of basically describe the same thing in a little bit more generality by just doing general G-gauge theory. So we have a general one-form symmetry group, two-form symmetry group, and then you can similarly write down an equation similar to what I wrote on the last slide, but in a little bit of a more general fashion. And I'm just going to gloss over this because of time.
Can I ask a question? So can you generalize this to have not here you have the structure delta A3 is B2 cup C2, but it could also be just a 4 co-cycle, like just an analog of this O3 that you had in the two group.
Yes. So was that your question, whether it's the analog or?
That's right, yes.
Yes.
And how would that sort of materialize in these gauge theories?
So I was going, so let me mention a little bit more about three-group symmetry generally. So first of all, I told you about two groups earlier. So in this context, the two group would involve the zero-form symmetry and the one-form symmetry. And there's a map from the zero-form symmetry onto the automorphisms of the one-form symmetry, and then there's a third cohomology class. And then the background field equations for this two group, if B1 is the background gauge field for the zero-form symmetry and B2 is the background gauge field for the one-form symmetry, then the H3 class appears in this way. And gamma 0 is basically this background zero-form gauge field written in this way. So this is a pullback of the third cohomology class. For the three group, then we have more information. We start with the two group, gamma 0, 1, and then we additionally have an extra group, which is this two-form symmetry group K2. We have a map from K0 on the automorphisms of K2, and then we have a fourth cohomology class. And now we somehow like the B1 and the B2, you can think about together with this equation are the same as defining, this is just like a flat background gauge field for the two group, satisfies, it's B1, B2 satisfying this equation. You can think about that as a map from our space-time into the classifying space of this two group. And so basically the analog of this equation that I had shown earlier is something like delta of B3, which is the background gauge field for the two-form symmetry, which is a three-form, is a pullback of a fourth cohomology class. And if you just forget about the zero-form symmetry, like what I did in the previous slides, then you really just have delta B3 is some pullback of a fourth cohomology class. And this is literally when I had written down this equation earlier. This equation is really just an example of this. So this right-hand side is really coming from a fourth cohomology class. It's coming from this fourth cohomology class. Okay, so I have we have a lot more results on now. You can include codimension 1 defects into the story, but I think I'll just kind of stop here. So you can write down like really full 3-group equations involving codimension 1, codimension 2, codimension 3 defects, invertible defects. So I'll just skip over all of that. And I just want to mention one last thing, which is that even though we have this interesting 3-group symmetry in terms of background gauge field, there's an interesting interpretation in the context of quantum error correction, because you can think about these gauge theories as examples of quantum error correcting codes. And the fact that we have this interesting equations for the 3-group, you can actually interpret them in the context of quantum error correction as there are some logical operators that you can define in terms of control Z gates and Pauli X gates and so on, acting on various submanifolds. And then these logical operators satisfy some algebra. And that algebra that the logical operators satisfy is just directly a manifestation of these background 3-group equations. So yeah, let me just end there. Let me just summarize. So the summary is that 3 + 1D topological phases of matter, they should have some IR or emergent fusion 3 category symmetries, which describes the algebraic structure of these defects, but we don't quite know what this object is. And we don't understand what kinds of physical behaviors it has. And at least the invertible topological defects, we have some almost complete understanding of by now. We think that they can be fully described by decorating submanifolds of a trivial phase with lower dimensional invertible phases and then gauging. But there's a word of caution here, which is a lot of times in a lot of what's going on in topological phases of matter and topological field theory, people conflate gap defects with topological defects. They're not necessarily the same thing. And this example of this twist string, which is geometric but not fully topological, is an example where you can have something that's gapped in a codimension 2 defect, but it's not necessarily what you would call a topological defect as a field theorist. So we can fully understand this 3-group, and there's many open questions. Like we don't fully understand how you derive the toothed anomalies of these 3 groups, and then we want to understand these non-invertible defects better. That's for the future. So sorry for running over time. Thank you.
Okay, thanks very much. Let's thank Maissam for his really nice talk. We had lots of questions, but please unmute yourself or put it in the chat. There's more questions.
So I have a question. Is there a lattice understanding of, you have these 1D SPT defects, right, which are codimension 2 in 3D
Yes.
model.
Yes.
So can you construct a 2D operator or a two-dimensional modification to your model, which is essentially a condensation defect of these 1D defects? Presumably that should be non-invertible, right?
Well, sorry, are you asking whether I can describe non-invertible codimension 2 defects?
No, a non-invertible codimension 1 defect, yes, which essentially is a condensation on a surface of the codimension 2 defect that you already constructed, which by modifying the lattice model by an SPT along a line.
Right. Yeah, that's a good question. I think so. We didn't study that. We did study these condensation, like the twist string, you can also understand as a condensation defect by summing over all the charge lines, the Wilson lines for the charges. So we'd have a description of that. But what you're saying also should be possible. We just haven't really done that construction.
Also, you don't look at SPTs in codimension 1 in 3D, or I guess you were going to say something about them.
Well, yeah, I didn't say much about codimension 1. So this is an interesting question. In codimension 1 in 3 + 1D, you could decorate with any invertible phase in principle, right? And you would get a gapped defect. But if you're doing TQFT, you might want the defects to be topological, meaning that when you insert them into the path integral, it doesn't matter at all how you move them around in space. And if you want your defect to be topological, then our understanding is that you should make sure that the chiral central charge is 0 of that 2+1D invertible phase that you're decorating with, unless that decoration happens on an orientation reversing wall, in which case you can allow non-zero chiral central charge. So this is another example of this distinction between gapped defects and what you would call a topological defect. And ultimately, this is because when you have a chiral central charge, there's some dependence on the framing, you have framing anomaly, and then all of that story.
But an SPT would still be like, it would be all right to.
That'd be fine. Yeah, that'd be fine. Yeah, you can decorate with SPT. Yeah.
It would presumably act on the charges. Like you had this picture where if you pull a flux through a twist string, it kind of wraps the twist string. So there'd be a similar kind of.
Yeah, exactly. That I did have a picture for that. So if you can have a codimension 1 defect labeled by a third cohomology class, and then you take your twist string, sorry, your flux string, take your flux string through it, and then you compactify your 2+1D system on a circle, and you get an effective 1+1D system, and then the slant product tells you exactly what 1+1D system you get. So the flux string becomes a flux string times a twist string when it goes through that defect, and that defines our action of the 0 form symmetry on the automorphisms of the 1 form symmetry.
And I have one last question, if I can ask. So can I think of this instead of locally modifying the Hamiltonian before gauging, can I do something slightly different? Can I start from something translationally invariant on a lattice, gauge in a standard way, but then think of these codimension, higher codimension operators, defects, what you have as defects in your picture as operators, topological operators, they somehow contribute to the symmetry structure of the gauge theory.
I don't quite understand the question. Indeed, you have symmetry operators that correspond to kind of sweeping these defects around in space. So, and you can do that all at the level of the lattice model as well. So maybe I didn't fully understand the question.
So my question was, instead of local modifications of Hamiltonians and then gauging, just gauge, get some translation invariant gauge theory, and then ask what is the collection of operators that commutes with this gauge theory. Right? That's the symmetry structure. Now, the question is, can one think of these SPTs and all of this? What were local modifications? Now, do they appear in the symmetry structure of a generic gauge theory?
Yes, you can do exactly that. You can just gauge it, get a translation invariant Hamiltonian, then you can look at the symmetries of that Hamiltonian. If it's a generic Hamiltonian, you'll want to look at the emergent symmetries, because you can always perturb the Hamiltonian by terms that kind of break all the symmetries. So either you're working in some idealized exactly solvable models where you have a lot of extra symmetry, or you need to discover kind of what the emergent low energy symmetries are. But let's say they're exact symmetries of the Hamiltonian, then indeed, if you find those symmetries, then you can just, instead of applying them on a closed submanifold, you just kind of apply them on a submanifold which has boundary. And then on the boundary, you'll create the defects.
Okay.
So actually that, like in this, when I was starting to do this quantum error correction perspective, that's an example. So, if there's like this, here I'm doing 2 copies of Z2 gauge theory. So we have a cubic lattice and we have sort of a red and blue layer. And you can do a control Z operation everywhere on a plane. And this control Z operation everywhere on a plane will give you, it'll give you like a symmetry of the ground state subspace. And that symmetry of the ground state subspace, you could then choose to apply it only on a surface which has boundary. And the boundary will be this twist string.
Thanks.
So I think
Can I-
Nadia had a question.
Yeah, I always have questions, but I feel like it took too much time.
Go ahead.
And I see Maissam already agrees with that. So there is a conjecture that I heard some people say that every TQFT in 3+1 dimensions is equivalent to a gauge theory, perhaps with a Dacre-Witten term.
Right.
Now, are your findings consistent with this conjecture, or disprove it? Or?
So yeah, our findings are consistent with that conjecture, but we're not really even so first of all, that conjecture, you should clarify, you could allow bosonic or fermionic charges. And what we're doing is we're not really probing that conjecture actually, because we're just starting with those class of phases or those class of TQFTs, and then we're asking what is their defect structure. And then we're finding the defect structure there is very rich for those class of theories. So I would say we don't really have anything to say about that sort of bigger question of, is it even true that all 3+1D TQFTs are described by G in a full closed cycle?
But along those lines, there are some which are actually not sort of a standard Dicke-Witten type theory, right? They have this, what Theo was last week calling this non-trivial Majorana layer. So the question is, in those cases.
Oh, fair enough. Okay, sorry.
Yeah,
So
I think there's a slight modification of that.
There's a subtlety,
right?
which is that if you have fermionic charges, it shouldn't be a new 4. It should be just some 3+1D invertible phase. Like, yeah, you're right. Thank you for the clarification.
So I think that statement has some refinement.
Yes.
Can I jump in with a quick question?
Yes.
So let's say you had a 3D theory with a two-form symmetry, with a two-group symmetry. And let's say I was trying to find the one-form symmetry, and I'm starting with the zero-form symmetry. So I know there's a two-form symmetry. I have a 3D theory. I have control over the zero-form symmetries. And if I want to recover the one-form symmetries of this two-group, I presumably would do something like what we do to calculate the 't Hooft anomaly, right? So I look at lines coming together, A, B, C, in two different ways, and I compare the obstruction to the different ways these lines come together to get a 3 cocycle. Is that the same thing as the Postnikov class for this two-form symmetry, for this two-group symmetry? Did the question make sense, or did I get my? I
didn't fully understand. So you have you have 3D meaning 2+1D, and you start with this zero form symmetry.
Yep.
And you're assuming that you don't know what the one form symmetry is?
Right. So I'm trying to recover the two. So I have a two-group symmetry, which corresponds to a 0 and a 1 form symmetry groups.
Yes.
I just know the 0 form symmetry, and I want to recover the 1 form symmetry from the physics. So I would, assumingly, I would just decorate like by like a web of lines meeting in my 3D space, and decorate my lines with elements of my 0 form symmetry group, and see how
you mean your sheets in space-time? You'd have sheets labeled by your 0 form symmetry.
So I'm thinking of my 0 form symmetry group taking values in the category. So these are invertible elements in the codimension 2 category. So the line operators.
Oh, those I think you'd say are the 1 form symmetries.
So then I suppose we have a 1 and a 2 form symmetry, right? So
no, you have 0 form symmetry and 1 form symmetry. 0 form symmetry describes the codimension 1 defects.
That's
and
right.
One form symmetry describes the codimension 2 defects.
So how would I? So imagine then. So I move everything up by 1. So imagine I had a 3 form symmetry. So I had 0, 1 and 2 form symmetry. So I have a 3 group. And if I had the 1 form symmetries and I want to recover the 2 form symmetries.
Well, are you going up a dimension as well, or are you staying in 2+1D?
I think I am staying in 2+1D. What I'm trying to do, basically, let me be clear. Let me go backwards. I'm trying to see the 't Hooft anomaly as some sort of obstruction cycle.
So, well, first of all, the 't Hooft anomaly is not this H3 class.
That's right. I understand that. That part was my question in the chat, but I want to see the relation of how this obstruction, is there an obstruction class? So 't Hooft anomaly is an obstruction class.
Yes.
Is there a way to think of that as some sort of higher symmetry?
Oh,
You mean categorical? You want to see what a 't Hooft
Yeah.
anomaly is between a zero
Yes.
form and one form. You can forget about two groups, for example,
Depending if
right?
the numbers work
Oh.
out. I always confuse myself with the numbers.
So one thing, so in this story, the way that the O4 obstruction enters is, probably didn't write the full thing, but I'm not sure this will fully answer you or satisfy you. But remember, I brought up this categorical two group, which
Right.
was basically this extra underline, which means that you have to carry around all this extra information that wasn't just in the two group.
Right.
And so what you can, and so similarly, just like here, we started with G and we promoted it into a two group in kind of a trivial way.
Right.
And then we asked for maps from G underline into this ought underline.
Right.
You can, so you can view these obstructions in the following way. First, you can imagine that you have a map from G with no underline into ought with no underline. So you have a map from G to ought C with no underlines.
Mm-hmm.
And then you want to lift that map to a map from G with underlines to ought with underlines.
Mm-hmm.
And the O3 is an obstruction to doing that because you need the O3s to match up. Now, then you can do one level higher. You can, now we saw that ought gets promoted to this thing with one extra underline, it's categorical two group. And similarly, you can promote your G with one underline into a G with two underlines. And then you could ask about lifting this map to a map where you have two underlines on both of them.
I see.
And
That's where
that's O4 will come up in that obstruction.
I see.
So this way of thinking about it was kind of described in this ENO paper. So you might, in a kind of an abstract way. And then our paper was kind of trying to work out like what exactly it all means exactly as terms of equations.
Okay. I'll think a little bit about that, but that's helpful. That's very helpful.
I think I can actually add something that would resonate with my understanding of the intuition that the last questioner asked. If you stay, say, in this example on this slide for concreteness, and imagine there is an anomaly. It means that under gauge transformation, the action is shifted by something. And the something is local, but it cannot be absorbed by a local counterterm. So you can trivially represent it by introducing also a two-form global symmetry. So two-form global symmetry in 2+1 dimension means roughly there is a three-form that you add to the action, and you postulate that its gauge transformation is exactly the one that cancels the anomaly in the lower form symmetries. And that can always be done. So any anomaly can always be canceled by adding a top form symmetry that can be added. In that sense, it fits into the same picture that appears here. Anyway, I interpret that as what you had in mind when you asked the question of whether the anomaly can also be thought of as some kind of a higher group.
Yeah, exactly.
So that sounds simple, but I think in the end, it is totally useless because it will not add any information beyond what you normally do with anomalies.
Or it's just a renaming of the obstruction in different terms.
That's right.
Yeah,
exactly.
I agree.
But it fits this general picture that you push things up in the form.
Thank you.
Okay. I don't see any other questions. Let's actually thank Maissam again for his really nice talk and discussions. I'll stop the recording. Of course, we can also stop the recording, and if people have more